Threat modeling is an essential part of an appropriate cybersecurity strategy. However, threats have to be understood at all possible levels, all possible layers of the OT computational stack. There is a misconception that operation technology security mostly means network security. So once we secure the perimeter, once we have proper firewall configurations, then we should be fine. And this is not true anymore because, as we've seen in the historical incident lecture, attacks have appeared at various levels, not only at the network level, but we've seen attacks affecting the firmware, or affecting the software, or affecting directly the control. So if we start seeing the computational stack, as we've seen also in previous lectures, starting from the hardware, firmware, control, software, network, and process, we have actually seen attacks appearing at different levels. So for example, the firmware level, the Ukraine attack, the power grid attack changed the firmware of the modems. Triton also changed the firmware of the Schneider electric safety controllers in order to be able to get special packets and get commands. So that was attack at the firmware. At the control level, Stuxnet changed how the control behave. Also changed at the software level, the HMI attacked Windows as well to be able to stay stealthy and evade detection. And network is what we mostly see with Night Dragon attack, one of the first ones that was mostly reconnaissance based, Flame and Havex, again mostly on the reconnaissance side. In the stack, we haven't seen attacks directly affecting the hardware, but they may have happened and we may not know about them, or at process at the unified level. So we've seen control attacks, but not so much something that synchronizes across different parts of the process to be able to deliver a meaningful process-aware attack. So let's go one by one, starting from the hardware and going all the way to the process to understand the possible threats in each layer and what are the possible mitigations that we can implement in each layer of the computational stack. So starting by the hardware layer. What do we mean by the hardware layer? We mean the exact components of the integrated system. We have CPU, ARM x86, we have memory, 256 megabytes, 1 gigabyte, 8 megabytes, the storage, the non-volatile storage, flash memory, network controllers, so on and so forth. I mentioned before, we haven't seen an attack exploiting hardware as of 2020 because hardware is very difficult to attack. But if you manage to take over the hardware, then you can mount a very powerful attack because the hardware is a root of trust. So any trust you have, firmware attestation, control level, like integrity checks, rely on the hardware being trusted. So possible attack vectors, to give examples about how you can attack the firmware, are side channels, use hardware properties such as electromagnetic emissions, timing, and power side channels to be able to extract information, to be able to do the reconnaissance side and extract directly from the hardware through side channels, either digital or analog. Hardware backdoors are a possibility. Again, we don't have documented cases, but since most fabrication, integrated circuit IC manufacturing happens in very specific, very few countries nowadays, so there is the possibility that someone can add a small hardware backdoor to your fabricated IC integrated circuit that can be used later on in the field for from attackers to gain access to your system. So hardware backdoors are also possible vectors to attack directly the hardware. Fault injection, you may have an encryption mechanism that performs some cryptographic primitive. However, you may cause some kind of a glitch, and that glitch can lead to a fault in execution of the cryptographic algorithm. And through analyzing the fault, you may get more information about maybe the key or maybe the plain text or the ciphertext that is involved in the process. And another example, final example, is Rawhammer. That's an attack that takes place in DDR memories. So Rawhammer, the way it works, it flips bits quickly in memory, and that flipping of bits is causing also surrounding memory cells to flip. And these surrounding memory cells may contain some information, for example, what is the privilege of the user in the system. So they may allow you to get privilege escalation from user, you go to root, and once you do that, you can take over the system. So Rowhammer attacks have been documented in the wild, but again, we haven't seen them in an OT environment. So that's for these are possible attacks at the hardware layer. Moving on to the firmware, we have seen firmware attacks. I mentioned them several times in the class. Definition of firmware is special software that provides the low-level control for a device-specific hardware. In the past, this idea of monolithic firmware would kind of contain operating system primitives in it, operating system controls, but now in modern control systems, modern ICS, firmware is kind of separate from operating system. It's more of the BIOS side, and then you have the operating system running on top. The Triton and the Ukraine Power Grid attack affected firmware, and the firmware attacks are also very powerful attacks like hardware, and because they are the lowest level of software you have. So you have an operating system, you have to trust the firmware to be able to have trust at the operating system level. And also they're much easier to attack compared to hardware. Hardware, you have to either be physically there or you have to interject in the hardware manufacturing process. In the case of firmware, you can remotely attack firmware through a firmware upgrade process or firmware corruption, firmware modification, and you can also erase your tracks in case you get detected. You can replace the original firmware so you won't be discovered. In the case of hardware, you cannot replace hardware. You cannot delete a hardware backdoor, because it's a physical thing, and it's very hard to remotely, probably impossible, to remotely erase a hardware backdoor. So attack vectors, firmware corruption, you completely corrupt the firmware so the device becomes inaccessible, it's bricked, or you can modify meaningfully the firmware in order to create some backdoor for you so you can access the system as you please. And that was the case with Triton, that specially crafted packets were detected by the modified firmware and allowed the attacker to send commands into the safety system. Going up the layers to the control layer, the control is responsible for driving the actuators in response to the sensor inputs. So we saw in the previous module, ladder logic, structured text, how you can create your control logic there. You have your input, compute, actuation, and this is what we mean by the control layer. Stuxnet is an example of attack at the control layer because it modified the control logic of the Siemens PLC in order to create some different actuation that was not the right one given the input to the system or given what the control logic has been, and the actuation was different. The control attacks are very powerful as well because they directly affect actuation, and actuation is affecting the process. They're difficult to mount, however, because for them to be meaningful and not just a denial of service attack, you have to have very good knowledge about the system. Even though we've seen them, there is suspicion that they were mostly they were instrumented by nation states. And they're discoverable. Since you're changing the process, it affects the process. There could be ways that you can discover the attack. In the case of Stuxnet, it was discovered by through suspicion of the decreased lifetime of the centrifuges. Attack vector, Stuxnet is one of them, controls misbehavior, or you can have even control unavailability. So your system is not responding at all. And you have a DOS attack in that regard that may cause further effects in your process. Moving up, the software layer is the most familiar to everyone coming from the IT world. We know what the software attack means. That's your standard software used to control and monitor ICS, but it's written in traditional programming languages. So you have your HMI running on Windows, or you have SSH access, you have FTP servers, Apache servers running your system. So the attacks that we have seen in IT are now applicable in the OT in the software layer side. Shamoon, for example, one of the first ones, affected Windows machines. The Windows machine was though located in an operation technology environment, but still there were Windows machines, so you can do attacks on Windows. And Shamoon erased, if you remember, the contents of the computers, creating a business continuity problem that had some effect in the operation of the utility. Here the attacks are easy to mount because you can just port them from the IT domain, and some we've seen Stuxnet affected also the HMI. Remember, it propagated through Windows machines to reach to the machine that had the HMI connected to the PLC. So remote code execution is one attack. SQL injection is what Shamoon did through the public-facing websites. He did SQL injection to enter the enterprise network and then propagate to other machines within the enterprise network of the utility. Going up from the software to the network side, this is where network security comes in. The ICS components are interacting with each other and also with the enterprise network in case of IT/OT integration via the network layer. So you may have your Modbus communication, DNP3 communication, firewall configuration is very relevant in this regard, and you may have demilitarized zone DMZ that you have created between your level 4 and level 5 and level 0 to level 3. Havex was malware that was probing devices at the network level. So Havex did not try to attack control, but it was listening it was eavesdropping on the buses of the control systems and was trying to find new devices to aid in the reconnaissance on behalf of the attacker. And now that we're moving towards to IP routability and maybe TCP for transport, it may be easier to explore, like Nmap, to explore networks through TCP/IP or other routing networks or transport networks, transport layers that we're familiar with. So once you're in the network, you can deliver many attacks. Man in the middle is one of them, or just reconnaissance Havex did. So these are the figure here is an example from Wireshark and how Havex was communicating, was pinging devices in the network in order to get more information about the network layout and what devices are there and what do they respond to, what kind of protocols they listen to and they actually respond to. That's on the network side. And finally, above the network, you have the unified process. So you have all these PLCs communicated, all these industrial control systems communicated with each other, but there's a final goal. We've seen in the past, desalination, for example, process. The final goal is to produce water suitable for human consumption. And the input is seawater, the output is water that will be distributed to the city for humans to consume. So that's the whole process, right? And you can think of process in the attack layer by thinking on how different you have to attack different parts of the system to be able to do some kind of a more advanced attack to the whole industrial process. We haven't seen any attack coordinating at the process level, even though the closest one that was Stuxnet, it did affect the process in a way that the uranium enrichment was affected. It was delayed to an extent, but it wasn't a coordinated attack at different levels. So we mostly characterize it at the control layer. However, I mean, these are just abstractions to help us think on how to protect our system from attacks at different layers. So if we suspect that there could be an attack that malware coordinates, we may have to find ways to protect against that. If we think that part of your our risk assessment is attacks to the hardware, we have to ensure that we get the hardware from trusted sources. We test the hardware before deploying it in the field. Same with this firmware. We're double checking the control. So the idea of the abstraction layers is to provide another dimension of guidelines on where we see the threats occurring. And process is the final one that we see things at the, again, unified process level. Even though we haven't seen real attacks, to the best of our knowledge, there are a few papers, academic papers, that show possible attacks that coordinate at different levels. For example, we have a paper in a workshop that will show how you can coordinate at different levels of the power grid to start creating some kind of a cascading effect that would eventually lead to a blackout. So academically, there have been a few papers that can be used for guidelines for seeing how you can be thinking about attacks at the process level and create defenses accordingly. So to conclude, again, let's stop thinking that OT security is just network security. We have to think about all the layers from the hardware to the process itself and ensure that we understand the threats at each layer and have appropriate mitigation mechanism applicable for the different layers.